he did for the PhD with Signe Render, and after that he came here for several years, I mean 4 years, no?
Almost 4 years.
Almost 4 years.
Yeah.
To work here at IFISC. And then he went to Macron Institute in Dresden for 2 years more, and back to Argentina. Okay. So he's an expert in non-equilibrium statistical physics, and today he's going to talk about optical dynamics. He will be here until the end of October.
3 more weeks.
Anyone interested in talking to me?
Thank you, Cristobal, and thank you for coming. So I am Federico Vázquez. I work at the University of Buenos Aires. And today I'm going to speak about the dynamics of opinion formation, and in particular about the phenomenon of polarization and also opinion consensus. So what you see here is a picture of one of the first computers in Argentina, also in Latin America. So the computer is all these models you see here, and it was brought from England to Argentina in 1960. Where? To the Calculus Institute. So that was 60 years ago, and now I think it's well known because they called it the first computer in the whole continent. Now things have changed, so maybe we're going down. But anyway, this is another story. That was a good time here. Okay, so the outline of the talk is the following. So first, I'm going to give you a first brief introduction with the motivation of this project. Then I'm going to talk about the model that explores the competition between two mechanisms, persuasion and compromise, that give rise to polarization. Then I'm going to speak a recent work where we studied the dynamics of voting intention. And at the end, I will just give a short summary and some conclusions. Okay, so public opinion polarization is defined as the formation of two social groups, that have very different or antagonistic or opposite opinions in a given spectrum. So you can think that people are totally in favor of something and other people totally against, so there are like two poles, opposite poles. And also the opinions become more and more different over time. So polarization is something dynamic. So there are many examples around the world. You can also see here in Spain, in the US, everywhere, about polarization. But me, I wanted to take this example, which is about the debate over the abortion law that is happening right now in Argentina. Okay. So there were many demonstrations in favor of the abortion that should be legal, secure, and free. Also demonstrations against, right? Many people in the Congress. Here is a picture of the Congress in Buenos Aires manifesting, in favor, also against. There were also many people on the streets. So this is one of the main avenues in the capital of Argentina, when you see a lot of thousands of people. Of course, this is a Photoshop. They, it's almost two different days. They march, different people, but actually, so they put it together. But you see, there's something really global, right? There are thousands of people, and now people discussing a lot about this topic. Okay, but me, I wanted to know something more quantitative. Okay, so I took this data that was published by the University of San Andres about a survey, where, so sorry, this is in Spanish because I didn't want to get it in English here. But so they asked people whether they agree or disagree with the law that guarantees an abortion that is legal, secure, and free. So the idea is that basically 94% of the surveyed people, right, they adopted one of these 4 possible options. They strongly agree with the law, they agree a little, they disagree a little, or they strongly disagree. So if you normalize by these 94% of people that actually decided for one of these 4 options, you get this plot that I made myself, where you can clearly see that the majority of individuals that voted, they adopted extreme viewpoints, right? Extreme opinions. Right? So almost 70% they are basically, or they strongly agree with the law, or they strongly disagree. And just around 30% are in the middle. Okay, they are moderates. Right? So this is a picture of polarization. Right? So really two poles well defined. Right? Almost they don't talk to each other, if you like. So, and another interesting thing that characterizes polarization is that the percentage of people in favor and also against are quite similar, right? It's very balanced. Even though the distribution is not symmetric, but still that is, it's quite balanced. Right? Okay. So the study of polarization is not new, right? Already in 1964, Abelson used a mathematical model to prove that if you have a population of individuals that are connected to each other and they interchange ideas or opinions, and they become more similar as they interact, right? They finally reach consensus. So they become more and more similar over time, right? Interacting, and they reach consensus. This is a mathematical model. However, he also noted that if you go to real life, the empirical patterns you see in real life are not the ones of consensus, but more of a polarization. It was almost more than 30 years ago. So Abelson in '64, in this nice paper, raises one of the fundamental questions in theoretical sociology, which is the following. What do we have to assume in the theoretical models, right, to generate the bimodal distribution of opinions, you see, as the one I show you right here for the abortion law. So what do you have to include in the mathematical models, right, to obtain this kind of distribution? Right. That's, I see an open question. The second question is, what are the mechanisms that explain how a group becomes polarized, for first principle? Okay, so more recently in 2012, Buenos and Lu, they published an article where they review many other articles where they use different mechanisms to explain polarization. But they arrive to this conclusion. They say that there are many models that show how groups arrive to consensus, but there are not general models that they show how groups become polarized. So they don't really know exactly. There is no universal mechanism. So that's why people have proposed different ideas. For instance, you have the mechanism of negative influence that you can see in real life. Somehow, individuals that are very different from each other, when they interact, right, they have very different opinions, kind of repel each other, right? So they become more extreme. And so they have a negative influence on one another. Even though you see this in real life, right, it was not supported by empirical evidence. Right? So there are no also experiments that confirm the negative influence. So then in 2013, Mas and Flasche published another article where they use the theory of homophily plus the theory of persuasion argument. And the idea here is that by homophily, individuals try to interact with similar others, right? So you try to interact with someone who has a similar opinion, and after they interact, they reinforce their opinions. So suppose that you have two individuals in favor of the abortion law, they interchange arguments and they become more in favor, right? So this is a kind of reinforcement due to homophily. So this induces polarization, right? So our idea was, yes?
You say negative influence, there's no evidence. How?
Yeah, this.
What do you mean?
Yeah, what I mean is, actually, this idea was a paper by Flasche that I talked to him a little bit. He did experiments, and then he published an article where you can see that in the experiments you don't see any real evidence of this, of the negative influence. Even as if, very common in real life, maybe it exists, but it's not that important.
I would say, in most or many countries, there are two main political parties, and if one party says one thing, then the other one says the opposite, just to be different.
Right.
And that propagates to the support.
Well, but this is one thing. The other thing is, here the idea is that they repel. So in an opinion spectrum, the negative influence means that they repel each other. They become more extreme. Right. So it's something dynamic. So, okay. So our idea here was trying to build, some models using statistical physics, and also trying to test all these theories in very simple models. And the idea was trying to connect the microscopic dynamic you see at the microscopic level with the behavior of the model at the macroscopic scale. And this is well done in statistical physics. So the model I'm going to present now is, we proposed it a few years ago. We published in 2 articles. When we're trying to test all these theories, right, or some of them. So in the model, the opinion will be an answer to a simple question. So if you talk about abortion, it will be, are you in favor or against legal abortion? You can answer yes or no. And then they ask you how much, right? So the opinions are given on this spectrum. So they are integer numbers from -m to m. So here -m represents an individual is totally against abortion, right? It's an extremist against. But then you can have also people that are strongly in favor, so they're extremists in favor, right? So you have a possible opinion spectrum and some moderates in between. A bit against and a bit in favor. So in the model, what you do is you pick, first you have a uniform distribution of opinions. So you have, let's say, 1,000 agents and you distribute it randomly, right? Over this spectrum. You don't know the outcome initially, right? And then you pick 2 individuals or 2 agents at random. Right? Say 1 and 2. Right? So suppose that person 1 has opinion J and person 2 opinion K. Both are positive, so both are in favor of the abortion law. So the idea is that they don't only say that in favor, but they exchange arguments. Right? They say why they are in favor. So for instance, person 1 says, I am in favor of the abortion law because clandestine abortion is one of the main causes of preventable maternal death. While person 2 says, well, I am also in favor because I think that a woman has the right to decide about her own body. So the idea is that now they exchange arguments, right? Person 1, they give the argument to person 2 and vice versa, and they have one more reason to be in favor of the abortion. So what happens is they reinforce their opinions. Okay. So person 1 goes from J to opinion J plus 1 and person 2 from K to K plus 1. So we say that this happens with a persuasion probability P. Not always happens, right? So this is somehow this intensity of the persuasion. And so we call it here reinforcement by persuasion, and we are using this argument persuasion theory proposed some years ago. Suppose that in the second case you can pick an agent that is in favor of abortion, but also someone which is against. So the person 1 can say, I'm in favor because abortion legalization might reduce maternal mortality, while person 2 say, well, I am against because abortion is morally incorrect. Okay. So now they try to reach an agreement in some intermediate opinion, right? So what we say is that there is a moderation by compromise, right? So the opinions get closer to each other, right? And so we say that here this happens with compromise probability Q, right? So these are the 2 parameters in model P and Q. So what you're using here is the social pressure proposed by Marson in '93. So now what we did is trying to study this model analytically and see what happens in the long time, right? And so for that we wrote equations for this for the time evolution of this magnitude xk, which is the fraction of agents that have opinion k, or density of agents with opinion k. So the equations look like this. They are gain and loss equations. For instance, this term xk minus 1 times sigma plus represents a transition from an agent that initially has opinion k minus 1 and increases opinion by 1, so it goes to k by interacting with a positive agent. So there is a gain term in xk, right, by persuasion. And here, for instance, you can have a gain term by compromise by picking an agent with opinion k plus 1 and then reduces the opinion by 1 and goes to k when interacting with a negative agent. So you can write all the equations, right? These are non-linear equations because sigma plus depends on xk, so you got xk squared. Right? So you cannot solve these equations exactly, analytically, but you can find the stationary state. And this is what we did.
So this assumes that everyone interacts with
everyone, yes. Yeah.
With everyone, or with only, well, interacts differently with the one with the same opinion and with the
right, exactly. So
opinions?
instead of this is a mean field all-to-all interaction. That's something that I didn't say. So you pick two individuals, anyone, and then the probability of change in the opinion depends on whether you are positive or negative, or one positive and the other one negative. That's the idea. So, so the solution is given, the stationary solution is given here. So it depends on R, and R is the ratio between the persuasion probability and the compromise probability. Right? So we call it the intensity of reinforcement. And you can see that it's an exponential in K, right? So this means that if R is larger than 1, so for instance 3, you can have a growing exponential. So this is the blue line that I'm plotting here, it's the formula. The red bars are the Monte Carlo realization and the stationary state. So you see I agree very well with theory. And this is the example of polarization as I mentioned before. So you see that most individuals, they are, they take extreme opinions, right? And there are a few in the center. Now, if you take R smaller than 1, you get something different. This is called centralization, so more individuals are moderates. They go to the center. Right? So somehow the reinforcement, what it does is reinforce the opinions of the same opinion individuals, so they go to the extreme values. Right? So kind of there is a force that is pushing the particles or the agents to the borders. This is more or less what's going on. Okay. Yes.
So the red thing is from simulations of the stochastic model.
Yes.
But that has absorbing states, right?
Yes. And that is coming now.
So this is not really the stationary distribution, right? This is a sort of metastable.
Yeah, this is exactly. It's a stationary distribution that the metastable state. Yes. Yeah, that's what I was when one slide before. So now if you do the Monte Carlo realization of this dynamic with 900 agents, there is something else going on, right? So this is R3. So you see that the dynamics is quite stochastic, as Tobias said, right? So you have, but you have still the polarization, right? But then you see after a while, but not very long, the symmetry is broken, so the positive agents start to drag negative ones, right? Like this. Until they kind of disappear, or disappear totally. And once they are all positive, they reinforce and they go to extremist consensus. So the actual outcome of the system is that there is no actually polarization, but it's transient. Okay? The final solution would be a consensus in, let's say, all supporting abortion, which is not very realistic in that sense. Okay. So what we see is that this model, even though it produces polarization that people observed before, is not very stable, right? So it's not. So if you expect wait for a very long time, the system reaches consensus, which is very different from what you see in real life. Okay. So also, if you have low reinforcement, right, you can see that the centralized state is also unstable. And so, very slowly just to see that there is also consensus in one. Yeah. And the final state depends also on the initial state of the system. If you have, say, more positive agents than negative at the beginning, then the final state will be a positive consensus. Okay, so conclusion, well, if you have a system when you have all-to-all interactions, the mechanism of reinforcement it doesn't lead to polarization, but is to consensus. It's very unstable. Yes?
Do you know how this scales with the number of agents? Is this transient time?
Yes, it scales as the logarithm of n is the number of agents. Typically, if you write the equations, once the symmetry is broken, it goes exponentially fast to the final state. So it goes like the log of n. Okay. So that's why we, Fatima, my former student, we're trying to see what happens if you have a population that interacts with a few others. You have a few neighbors to interact, okay, instead of all. So we studied the same dynamics, but on a square lattice, okay? And in the case of m equal 2, you have only 4 opinions, like 2 extremists and then 2 moderates, okay? So the rules are exactly the same, But now the only difference, as the previous model, the only difference is that you pick two nearest neighbors in the lattice. Okay, for instance, this I and j with probability p, they go to say minus 1 minus 2 to minus 2 minus 2. This is the persuasion event. And for instance, in the compromise event, you pick the two neighbors over here, they go to these two states. So the rules are the same, but you pick only nearest neighbor. So now we're going to see the results. Now I took 10,000 agents, we are 3, so then you should observe polarization, right? And this is exactly what happens. So you see that, first the system gets quickly polarized, right? Also the level of polarization is quite high because it's almost 95% they are extremists between these two. And the third thing is that the polarized state lasts for a very long time, right? So the idea of putting this on the square lattice is that now the polarized state becomes very stable. Right? That was one of the main conclusions in this part. So here I'm trying to compare, so if you run this simulation, I think it lasts for a very long time. So now if you run the same dynamics, but on all-to-all interactions, also with the same parameters, 10,000 agents and R3, you get that the polarized state is not very high and also is quite unstable, just to compare with the lattice. Okay, so now I'm going to show you what happens in the real lattice. So this is what Fatima did. She plotted actually this animation of the model, starting from a uniform distribution of these 4 opinions. There is a domain coarsening. So if you are familiar with the AC model, you see that it's quite similar. You have the formation of these domains. So here blue is opinion +2 and red is -2. So these are the two extremists, and the moderates are in between, right? So at the interface between the two domains, right? So the only difference, difference with the easy model here is that we have 4 states instead of up and down spins, and also there is no temperature in the model. Right? You have a very similar dynamics. So now I'm going to show you another. This is one type of realization, right?
So you say there is no temperature, but you have probability of doing. So if they interact, they not always go to one state. They can go to. They can remain stable
right.
in the same place. So
yes.
This is temperature. This is a.
Well, what I mean, temperature is a stochastic fluctuation. You flip someone, an agent at random, basically.
It's not random, but the outcome of the interaction is random. You have some
right.
probability of doing something.
Well, yeah, in that sense you have fluctuation. Maybe you have to associate it with temperature, but it's not straightforward. Also in the AC model, you have inside each domain, you have flipping events, right? This is noise in the bulk, it's called.
Depending on the dynamics, you have conserved dynamics, you don't.
Conserve, you mean the Kawasaki dynamic, okay. Well, that's what I mean, the original easy model.
Glauber model. The Glauber model.
The Glauber, with the Glauber dynamics, yes. Well, in this model you have domains inside are frozen, right? There is no interaction. Okay, so this is another type of realization. There is something else. Oh, well, I went too fast anyways. Okay, so you have another, the same initial conditions, you get something different, which is the formation of diagonal bands, right? Let's speed up moving. So it seems that the system goes to this quite a stable configuration, right? And this doesn't happen very often. Maybe 2% of the realizations go to this kind of configuration. Unfortunately, this is not nothing new, so people knew it from Ising-like system that presents also this phenomenon. And okay, and then you have a third type of realization that this is quite often. Well, this is 30% of realizations. They go to this kind of straight line, also pattern. This is the formation of horizontal band. So once this band is formed, then the system is quite stable, because you see that in order for this to reach consensus, this interface has to diffuse and meet the other interface. Right? So you can think that the two random walkers that diffuse slowly until they touch. Right? And then the band is broken and the system reaches consensus. So that's why the polarized state is very stable. Right? That's the reason, at least in lattices. Okay. So
you say the polarized state is stable only you reach a straight band. You have courses only with some of the...
Exactly. In this kind of configurations, it's quite stable. I get stuck in this. Yeah. So, in fact, maybe related to what you were saying, you have this, if you measure the time to reach consensus versus the number of lattice sides, n, so the consensus time scales as n in this type 1 realization, when you have domain coarsening. Right? But then, if you go to type 2 realizations, these bands, so it scales with a much larger exponent, 1.71. Right? So now if you combine these two exponents, you get something in between. So what we found in the literature was that, so this is a very weird exponent, right? It's not 1.5 and not 2. So, and we found in the literature that there were many articles from 87, also people that here Maxi with Xavi Castelló published very related articles where they find a very similar exponent, 1.68, 1.72, right? But they didn't know how to explain this. So that's why we tried an explanation of this non-trivial exponent, right? Trying to study the dynamics of the interfaces, right? So you set the system with the initial vertical band, then you let the system go, so you have this formation of this rugosity. Then these interfaces diffuse like this until they meet and break. So maybe I can show you a picture of this. I'm sorry, picture. So these are what happened at the very end of the realization. Speed up. So this actually takes a while because the two interfaces have to diffuse, right, until they meet. But you can consider that the most time is spent in the diffusion of these interfaces. That's why it takes so long. So that's why we approximated the mean consensus time, the time that it takes the two interfaces to meet by the first time. And this is kind of known in the literature as a first passage problem. So we have this problem here, the two interfaces, a diffusion. We have a width that for now we don't consider, right? And consider the two interfaces are like 2-point particles. They diffuse until they meet, right? So the time to meet is known, is scaled as L squared over 16dl. L is the length of the interval, right? And the L is the diffusion constant that goes like 1 over the lattice side, right? So the longer the interface, the slower the diffusion. Right? So when you plug this diffusion constant here, you get L cubed, right? And this is the first approximation already done by Chen and Renner in 2005. That's why we propose a second approximation. So this is okay. So here I compare, the approximation one. This is the dotted line here with the simulation, the dots. And you see that exponent 3 is very different to 3.42, right? And this is the power law you obtain more or less here. So it seems that when L goes to infinity, the Monte Carlo simulation goes to this exponent 3. There was something people were arguing this. And we actually checked this. So the second approximation we propose is that now we consider the width of the interfaces, right? The interface has a width here, delta x. So now you have the diffusion of two rods, right? They diffuse like this until they meet by the first time. So if you consider the width of each interface, or the length of each rod, now the rows diffuse in a shorter interval. L bar, we call L minus 2 delta x, right? Effective interval. And then you can use the same formula at the meantime, but now you put L bar square over the L. And then L bar will be L minus 2 times the width of the interface, the mean value of the width of the interfaces. That is known to scale as L to the exponent power similar to 0.5. So you can see also that this is in the universality class of the easy model, that so the width increases from 0 with time until it saturates a value that is grows as square root of L, okay, more or less. So now when you plug this value over there, you obtain the second expression, right? You see that, so you have the L cube, but it's modified by this prefactor over here. That give you a second, a power law or exponent that is larger than 3. Okay. And this is what I'm plotting here. So this is the pink line, second approximation. The blue is the Monte Carlo simulation. You see that agrees very well now from L larger than 16. And also, so first of all, it says that there is no, people are measuring some power law that it didn't actually exist, because the exponent was changing, very slowly with L, right? So you will measure in a range that you obtain something 0.4. But then also when L goes to infinity, it seems that, well, this goes to 0 and you recover the power 3. Okay? That's the conclusion. So to summarize this, the first part, we studied this very simple model that explores the competition between persuasion and compromise, and leads rise to polarization, that is transient, when persuasion dominates, and also to centralization when compromise dominates. But at the very end, you obtain this extremist consensus. Now, if you study the same dynamics on square lattices, we have the formation of these domains, this coarsening by curvature as in the easy model, right? That's why the polarization becomes very stable. The consensus time is very long. And you obtain this also non-trivial or anomalous exponents, 164, if you combine the two types of realizations, that can be explained using taking into account the roughness of the interfaces. Right? Okay, and explains these works here. Okay, so now in the last, the second last part of the talk, we will talk about this model. So we recently almost published this article in Physical Review. What the idea was, with Pablo, was trying to forget about these theories of persuasion and anything that is in the social literature, and make a model, a very simple model that also induces polarization. Okay. So the idea here is that the population also have to decide between their with abortion or against, yes or no. Suppose they have to vote, so they have two alternatives, yes or no. But before the election day, they develop a propensity or an inclination to choose, let's say, yes. And we call this propensity P, right? So in these examples, P is close to 1, let's say 0.95 is here. So this person is going to vote for yes, almost for sure. But if P is close to 0, say 0.01, this person is going to choose no. Now, if someone has a P in between, it's undecided. Right? He doesn't know. All right. So the idea now is that you pick two agents also at random, is all-to-all interactions, I and J. So with propensity Pi and Bj. So then I ask J who was going to vote for. So J says that he's going to vote for yes with probability Bj. So that's why I increases the propensity in H. So it goes from Pi to Pi plus H. So it's kind of convinced by J. But also, J can say that it's going to vote for no, because it doesn't really know, right? Because its propensity is not exactly 1 or 0. So with probability 1 minus Bj, J says no, so I decreases the propensity by H. And H is a fixed length step. Right? So in general, we say that the probability of increasing or decreasing the propensity is a weighted average between Bj and Bi. Right? And we call the weight omega is the weight of self-propensity. Right? It's the weight assigned to its own propensity. So it means that if you interact with someone and omega is 1, means that I don't care about my neighbor, I just care about myself. So you put all the weight in yourself. This is a 100% selfish model if omega is 1. Now, if omega is 0, will be a totally non-confident model. So you don't trust yourself and you put the weight on your neighbor. Totally, right? Okay, so we study what happens when you vary omega from 0 to 1. So again, you start with a uniform distribution of propensities, and this state is not polarized. We use, for instance, omega 0.5 when you do a single average. Okay. And as we did previously, we studied the system by writing equations for these magnitudes nk, which is a fraction of density of agents with opinion k, k times h.
What happens at the borders? Let's say,
yes. So once you have, let's say opinion, say a propensity 0.95, and then by increasing h, you go outside the interval, you put it in 1. So that's why. So we have a constraint between 0 and 1.
But maybe then when you approach the border, you do it with a finite velocity or something, no? You don't stop progressively.
Well, yes, I mean, no, you go, suppose that h is 0.1, so you go, suppose that you got 0.65, 0.75, 0.85, 0.95, and then it's 1.05, you go back to 0.1. Yeah, actually this is, the analytical solution of this problem is very difficult because of the boundary conditions. So it's very weird, the dynamics right at the border. So that's why we did something analytically in continuous time and age. But it's, so the idea of putting this boundary condition was a headache, actually. So instead of, Another thing is that also so you start with a uniform distribution of propensity, but then because once they reach the border, the propensity is 1, then it will be 1 minus h, 1 minus 2h, so there will be multiples of h, right, after a few steps. That's why you have, let's say, S, which is 1 over h possible different propensities. So the equation, it looks very similar to the model I presented before. Also, these are non-linear equations because you have, for instance, nk minus 1 times m, and m is the mean propensity, so that depends also on nk, so you have nk squared. So we found this, the stationary solution of this system, and it looks like this. So this is, nk will be this function over here, it depends on the ratio between the gamma functions times n0, and this is what I'm plotting here right now. It's a pink and also the bars are the Monte Carlo realization. So you can go to the, I'm not showing here, to the continuous limit where h is very, very small, and it's very interesting because you get a convection diffusion equation, right, where the convection is negative, right? So negative means that if agents are right here, there is a force that drags the agent to the extreme. So there's a force that pulls the agents to the propensity 1 or 0. Right? And the solution of this equation gives an inverted Gaussian. This is right here, the inverted Gaussian will be e to the plus p minus 1/2 squared. That's what I'm plotting. Okay. And this is more or less the dynamics. It's a bit more complicated than this, but I show you this photo. It's easier. So we have two fixed points, right, corresponding to consensus in 1 and in 0, 1 and 0, and then a non-trivial fixed point here corresponding to the polarized state. So I didn't say that. Okay, so this model also induces polarization, right? With omega is already 1/2, right? And the level of polarization increases with omega, right? That I'm going to show you later. So, so these non-trivial fixed points correspond to this polarized state, and it's a saddle node point, right? So it means that if you start from any symmetric distribution, right, around half, so for instance, the uniform distribution is symmetric, you go directly to this point over there, which is this distribution. But as long as you deviate a little bit from this symmetric distribution, you go to one of the fixed points over there. So again, as it happens in the previous model, there is the system is very unstable because even if you start with a perfect uniform distribution, the fluctuations, stochastic fluctuations, make the system to leave this symmetry, so it goes finally to one of the points. One more thing that we recently discovered is that even if you don't start with a symmetric distribution, you get something that is asymmetric, but it's not trivial. You can go also to this fixed point. Right? Okay, so this is the Monte Carlo realization. So you see that as was happening before, there is, the polarized state lasts for quite a while, but then at the very end, it reaches extremist consensus. So we have the same problem as before, that is quite unstable. And we're actually looking for a mechanism to stabilize within the mean field equation to stabilize this polarized state, but it seems that it's not straightforward finding a mechanism. Okay, so last thing we did was to study the level of polarization as a function of omega. So define as the ratio between the width of the distribution, right, versus divided by the width of the uniform distribution. So when the system is polarized, the width increases, right? So this ratio will be larger than 1. Right? And this is what I'm showing here. That's what I'm showing here. So you see that this is the polarization level versus omega. So the weight omega is 0, the system doesn't get polarized, right? So this is 1 here. But now, as long as omega is larger than 1, even a tiny bit, let's say 0.1, it's already to polarize the system. So this means that this is a natural state of society because, let's say, omega 0.1 means that you put the 90% of the weight into your neighbor when you talk to him, right? And even in this case, the system gets polarized. So that will be the natural state of a society within this model. Okay, just to summarize and the second part and finish. So we studied this very simple model, and the conclusion is that if you assign a tiny weight omega larger than 0 to the own propensity, it's enough to polarize the system. So we find in the literature that this model or this conclusion has an analogy with the Schilling model, like he proposed in '69 for segregation. Schilling was a Nobel Prize winner in economy in 2005, I think. In '69, he proposed this very simple model to explain the segregation of the racial segregation in Chicago, right? Where you see, white, black, Mexican, or say Asian populations. And the idea is that basically a person will move out its neighborhood if the number of individuals with a different race will overcome a threshold value. So they say, well, if let's say 80% of my neighbors are not of my race, I'll move out. Right? So even if you put a very high threshold, so you're very tolerant, let's say 90%, Schilling showed that this model produces segregation. Right? So that will be the natural state of one society, to be segregated. Okay? And well, even if we almost published this article, we are still working on some analytical solutions. And before I finish, I want to thank my collaborators. So Fátima Velázquez Rojas, now she's working in La Plata. Cristian and Lydia from the University of Mar del Plata, and also Nicolás and Juan Pablo from the University of Buenos Aires. And I thank you all for listening. Any questions or already asked?
Professor, according to you, the dimension of
you do the model in a lower dimension, the system stabilizes, so the polarization is
Yes.
But this is contrary to, for example, for the result of the water model, let's say, because in the water model, in all-to-all, the system stays in a stable solution. Well, not stable, but when you